You ready for something harder? I gave this to some course. Maybe it was a 3101 test. Not test, but assignment, right? So what's, in fact, my father, you might know, is a mathematician, and his wife is a mathematician. And we were standing over maybe Thanksgiving dinner, and she was saying what a homework assignment she gave. And her way of proving it was completely different than my way of proving it. She's coming from a graph theory world, and I'm coming from an induction. And I wasn't even convinced what she was doing was right. So we had a big argument about it, right? So here I'm teaching you. We're not going to do the actual graph theory. We're going to talk about what's the big picture of how I would, recursion and induction does it. All right. So anyway, you don't even have to read these things. I put the words up so that you can look at them slowly. What is a planar graph? What is a graph? It's a bunch of nodes with edges between them, right? You all know that from 1019. What's a planar graph is you can draw it in the plane where no edges cross, right? So those are planar graphs, right? What's a coloring? I give every node a color so that some nodes can have the same color, but they can't have the same color if there's an edge between them, right? It's kind of like I want to schedule courses to time slots, and every course has to go to a time slot, but two courses can go to the same time slot, but not if the same people are taking it, right? So that's graph coloring is important. And this claims, those are all planar graphs. What we want to prove something like for every planar graph, right? And remember the game. So we playing the game here, right? You give me some planar graph. I can find some node in the planar graph with low degree, right? Degree less than 5, right? So you'll look in all of these examples, right? Here's a node of degree 3, right? Here's a node of degree 5. Now there's always can be a node that has high degree, right? But there's always at least one node with low degree, right? People kind of understand the statement, and you have to be able to know. This is where I'm saying you need to be able to know the language to be able to start, right? And I think so. My little brother Alex was over yesterday, and we had a great time talking about machine learning and research he might do in Oxford next month. But I might have told you the story. He came to me once with set theory, where you have arbitrary subsets of the real, scary things, and he couldn't prove it. And I said, well, let's first write it down as a first order logic statement, and then prove it like this game, and it all fell out, right? So if you take a graph theory course, they're going to write it down in English, and I'm saying write it down in first order logic, and so you make sure you understand what's happening. And thinking about the game, right? The game here is some adversary gives me an arbitrary graph, right? And now my goal is to find a node that has low degree. And I'm promising you I have an algorithm that can find a node of low degree, right? And what did we do? We just brought it over to computer science, right? It's now an algorithm where you give me a graph, and I promise I have an algorithm that's going to find a low degree node, right? Does that make sense? So that right there is where the difference between me and my stepmother, where I'm thinking about it computationally, right? And recursively, right? Right. So, and then we can say more. What's a coloring? Coloring is you give a color to every node such that for every edge, they have a different color, right? You have to say, I give you a coloring such that the adversary can give me any two nodes, and look I didn't color them the same, right? Right, and then we can go further and prove that every graph can be colored with 6 colors, right? And so here, I guess what we are going to do is we have an oracle that's assuring us of this, all right? So we could prove that. You can look up, I could give you the proof of it. It's not very hard, right? You do induction, you prove it by induction. Oh, in fact, remember in 1019, you did the strong induction stuff, right? You had this weird structure and you took off bits of it. So what we're doing here is strong induction, right? You're going to prove this by strong induction, and then once you have this, we're going to prove this by strong induction, right? All right. So this is just saying in 1019, people wrote these proofs on the board, and did you follow it? There were so many moving parts, right? When did they say, let this be arbitrary? When did they say, hey, right? I'm saying, had you done this first order logic game, there wouldn't have been so many moving parts, right? Right? I think if you went back and looked at their proof, there would have been adversaries and provers and oracles. They just didn't use those words, right? Right? So, and you know induction, we're doing induction. And, right, so what's the high, if they were going to give you just the high level of the proof, we're doing induction. So you want to prove that any planar graph with I nodes can be colored with 6 colors, right? So when you do induction, you know it's true for I minus 1 nodes, and you're given a graph with I nodes. So what you have to do, you have to take this structure, that's why it's structural induction, this graph with I nodes, and remove one of the nodes, color it by your oracle, and then put the node back in, right? That's what we're going to be doing. And then what do you need to know? To know which node do you delete? Well, you delete a node with low degree so you can put it back in. All right? And it does boil down to if somebody tells you a math problem, you write it down in first order logic. And why do you do that? Well, because it's a really good language for expressing these things. And in fact, it's surprisingly good. You think, oh, well, what happens if I want to say something else? Well, surprisingly, you can say, I haven't found anything in math that you can't easily say in this language. All right? And then you parse this thing with the grammar so you know how it looks, and you mechanically play this game. All right? And that's all we're going to do. All right? So what we're going to do is we're going to write down every first order logic sentence that we say, and we're going to make sure we know how to play the game for it. And then we're going to merge all those games together and get a proof for this problem. All right? So what's induction? And holler if you're at all not following. All right? I really, at this point, don't know whether this is going to be too easy for you or too hard for you. Right? I really don't know. All right? So induction. Right? We can parse it while playing the game, right? The top level is this implies, right? So what do? Is when we use it, we prove S0 in the inductive step, and the oracle gives us that it's true for all I, right? How do we do those things? Well, we have to, now it's an and. How do you prove an and? Well, we prove the S0, and then we have to prove this other piece. How do we prove this other piece? An adversary gives us an arbitrary I. We need to prove this implies. How do we prove this implies? We're given an S, we're assured by the oracle that S of I minus 1, and we have to prove S of I, right? And then we get what we want. All right, so everybody good with that? Right, and now, right, when she assures us of it, right, then I can give her any I, and she'll assure me that S of I is true, right? So that's the parsing of this guy. You should know how to parse these things, right? All right, now what are we saying? We're saying any simple undirected graph that's, oh, what's the definition of planar, right? You have to think, what's the definition of planar? Well, you can embed it into a 2D space such that no edges cross, right? So what's the definition of planar? Here, you want to write it down. You want to say, why is it planar? Because there exists an embedding. Here I call it E for you spell embedding with E, not I, right? And so if I want to prove to you that it's planar, then I have to give you, oh no, here I guess she's assuring we're doing it yellow here. All right? So in yellow, the oracle's assuring me that it's planar. And if she assures me it's planar, she gives me an embedding. And then I give her a pair of nodes that has an edge. I give her an edge, and she shows me a pair of edges. Sorry, it's not a pair of nodes. She gives me a pair of edges, and she assures me that those edges don't cross. Right? Does that make sense? All right. What? Now here's something we know about planar graphs. Right? The proof's not hard. I certainly have it on one of my web pages, right? What do we want to say? What does it mean? She's assuring us this statement about planar graphs, right? Because somebody else proved it, right? She's assuring us this statement here. What does it mean? It means for any planar graph, you give, right? So for all planar graphs, I can give her an arbitrary planar graph. And what is she assuring me? She's assuring me that there exists a node. So where does that node come from? She gives me a node, right? And then she assures me that the degree of that node in the planar graph is at most 5, right? Everybody follow this? For every planar graph, anybody can come up with a planar graph. And then the oracle will give us a node that has degree less than 5. Right? Everybody following these games? Right? All right. Now, my goal is to prove that every planar graph can be colored with 6 nodes. Right? So what's that statement? That statement says, how do we prove it? Right? In fact, this should have been part of the right top level. I think we just lost power, right? It went kind of quiet. It went red. Oh, no, we got red. It could be the man who came to see us last class. Some class said they change these batteries every day. These batteries are not changed. Hello, no, these batteries are not changed. All right, do we know how to get into What?
They're just trying to hit speakers. Your speakers right now will cause feedback stands.
Yeah, well, that's, I mean, I can think about one thing at a time. Hello, can you hear me? Anybody know whether you can hear me on yours? You should, I should have gotten somebody else up here. Anyway.
Yes. You're audible.
Okay, good. All right, I'm talking. Now, yeah, I'm working on it. Okay, anyway, I turned off this mic. All right, I think we might be good. All right, so what do we have to prove? We want to prove that every planar graph can be colored with 6 nodes. So how do you prove it? You parse this thing. It's what's the top? It says for every planar graph. So you give me an arbitrary planar graph, right? And then what do? I have to construct a coloring, right? And then once I construct the coloring, I have to prove 2 things, right? There's an and here. The and is I have to prove that my coloring assigns every node a color, and the number of colors assigned is at most 6, right? And then I have to prove this, the for all. It's a for all. So how do I prove a for all? An adversary gives me an arbitrary edge, and I prove that the colors on that edge are different, right? Everybody buy this, right? See what, if the key, really, if you don't learn any formal proofs, we'll live. But I really do think you have to be able to understand these statements from a first order principle, right? All right, so now what's our statement? Our statement, we're going to prove by induction, S of I, that every graph with planar graph with I nodes is 6 coloring, right? So here we're adding the statement S of I. And what are we saying? We're saying for any graph, if the graph has I nodes, then I can color it, right? Everybody good with that? All right, so the adversary gives me an arbitrary graph, and then somebody, either the adversary or the oracle, somebody assures me that the graph has I colors. Has I nodes, right? All right. All right, so now let's see. What are we doing now? All right, so now what we're doing is we're combining the things that we know, right? We know induction, we know the degree of planar graphs, and our goal is to prove planar coloring, right? So here's the induction, here's the planar graph statement, here's the coloring problem, right? And we're just now going to play the game that we have an oracle for this, an oracle for this, then we can prove this, right? All right, so, right, first we do induction, right? We prove S of 0. And then we prove right? All right, so how do we prove S of 0? Well, we're talking about the graphs with no edges, right? Sorry, graphs with no nodes, right? Well, are all the elephants in this room pink? Yes. Is there a coloring that colors them all? Well, the coloring that doesn't give, there's no colors. Are all edges bichromatic? Well, there are no edges, so they're bichromatic, right? Everybody good with that? All right, now I have to prove S of I. All right, so here, look at, we write down what we're doing for the two different, here's the oracle, right? The oracle's assuring us that all graphs of I minus 1 colors are planar, right? And we have to prove that all graphs of I colors are 6 colorable, right? Everybody get that? She assures us that I minus 1 node graphs are colorable. We prove that I colors, right? So here, and you see these two trees have different colorings, right? Why? Because one is being assured to us, and one the prover is proving, right? So everybody get that? So we're going to play these two games merged together. All right? The roles, we got our roles, right? This is just in case I were to do this to other people, they don't know what my colors are, right? All right. So, and we're going to play the game in order to prove this statement, right? And what do we need to do? Right. So we start off here. How do we start off? If you're doing this in 1019, hopefully they said, give me an arbitrary graph that has I nodes, right? Where does it come from? It comes from the adversary, right? Why an adversary? Because it's a worst case. It's not, we're not trying to prove random graphs or graphs that I like. We're trying to prove worst case graphs are colorable, right? So we're given this worst case graph. And then, and somebody assures us that it has I nodes. And then my goal is to prove that it's colorable, right? And how do I, all right, so here's a little panic man. I don't know if you know the idea of NP complete, but there is a class of problems that we don't believe have quick algorithms. And one of them is graph coloring, right? So there's not a quick algorithm for just doing graphs in general. But luckily, we know it's planar. And luckily, we have an oracle, right? So there are algorithms for coloring. In fact, what we're going to be doing now is describing a recursive algorithm, right? Induction equals recursion. Recursion equals an algorithm, right? So that's what we're going to be doing. All right. So we're going to go over to our oracle, and we say, oracle, you claim something about every graph, right? So she's saying you can give me a graph with I minus 1 colors, right? And what will she do? She will color it, right? So how do I get a graph for her? I have a graph with I nodes, right? Right here, you see right here, I have a graph with I nodes. And she wants a graph with I minus 1 nodes. Remember what we did in all the tests is I gave a hint, and my hint was divide the number by 2, right? Well, now my hint is take off a node, right? This guy gives me a graph of I nodes, and what am I going to do? I'm going to delete a node. Which node am I going to delete? Here you see. Here's my graph. I'm deleting a node with lowest degree. And I must admit, when I looked at that, I say, well, that doesn't look very low. But the truth is, if you count, all in this graph, all nodes have degree 5. So it's whatever, right? So we're going to delete that node, right? And really what we're doing is deleting a node of degree 5 or less. And we know that there is such a node, right? So here, let's pop over to our oracle. Remember, we need to use an oracle. Our oracle has to say that there is such a node, right? Our oracle's assuring us of this. So what do? We give the oracle our graph with I nodes that we got from the adversary, right? And she gives us a node of degree less than 5 or less, right? Everybody see the game? The adversary gave me this graph of I nodes. I give it to this oracle. Oracle gives me a node of degree 5, right? We're just playing the game. All right, so now what am I giving her? I'm giving her this graph G prime that has I minus 1 nodes, right? Now, a little side here is I have to make sure I'm giving her a planar graph, right? So I go into this is, and we could go back into, I don't know if we go back into the definition of planar graph or not, but here, in fact, let's see if we do. Oh, sure enough, we do, right? So here, she's assuring me, the adversary maybe, somebody's assuring me that the graph I got from the oracle is planar, right? And I have to make sure that my new graph with one less node in it is planar, right? So how do I prove it? I have to prove G prime is planar. So how do I come up with an embedding? Well, I go over and get the embedding for the bigger graph, right? I take the embedding for the bigger graph. And what do? I remove from the embedding the node that I removed, right? And then I have to prove that every pair of edges doesn't cross. How do I prove that? Well, over here, the adversary gave me a pair of edges, and I have to prove they don't cross. So the adversary gave me a pair of edges. I give them over to my other oracle, right? I give them over to this oracle, and she assures that in the bigger graphs they don't cross, right? So they don't cross in the smaller graph, right? Everybody buy that, right? And do you need to go through all these steps? Well, somewhere in your brain, you're going to say, if the bigger graph is planar, then the smaller graph is planar. And somebody asks you why, you'll say, well, any embedding I get from the bigger graph is going to work for the smaller graph, right? It's not rocket science, but somewhere in there, in your brain, you're following this game, right? Does that make sense? You know that you're taking an embedding from the one promise and giving it to the other promise, right? All right, so now we're back here and we have the right number of nodes. Why do we have the right number of nodes? Because we took away a node, right? This guy's promising us that we have I nodes. We took away a node. So we're promising we have I minus 1 nodes, right? It's all in there. All right, now, what is she doing for us? We gave her a graph with I minus 1 nodes. What does she do? She gives me a coloring, right? There it is. It's a beautiful coloring of this graph. And what do? What do I have to do? I have to come up with the coloring of the full graph. So what do I have to do for that? Exactly. Right? I put the node back and give it a color. Right? What color does it get? One of the 6. right? I only have this node here. Where is it? This node down here only has 5 neighbors, right? So the coloring I got from my oracle only has 5 colors on those 5 nodes. Well, maybe there are even fewer colors because these nodes might be colored the same. I don't know, but at most 5. So there's a 6th color. Yeah.
Could you confirm just what the coloring scheme is? Is it based on the degree of edges per node, or what is it?
We don't know. We're given an arbitrary coloring from the oracle, right? This is an and we're promised that it's a coloring, right? And all right? It's like recursion in general. I'm going to say what you're doing is micromanaging your friends, right? You're saying, oh, what is my friends doing? Don't micromanage your oracle either.
Wouldn't it be possible to have a coloring with anything of 6 colors with any graph that has 6 or more by the pigeonhole principle? You know, I mean, as long as there's 6 nodes, you can make 6 different colors. You just can't do anything less than 6.
No, no, maybe you're missing the big point. The question is, can you color with 6 or less colors? The question is, do you need, they're graphs. In fact, there are graphs whose all their degrees are 3 that need lots and lots of colors. Right? It's a question, do I need that many colors? Right? Can I color it with 6 colors? Well, if I can color it with 6 colors, I can color it with 7 colors. That's not the issue. The issue is, do I need 6 colors?
Oh, can you do it with less?
Or less. I don't care. If you can do it with 5, I can do it with 6.
Can you always do it with 1?
No, because every edge needs to be bichromatic.
Oh, sorry, I missed that definition.
Oh, yeah. Here's the key, right? I mean, another way of thinking about it is course scheduling. I need to assign every course a time slot. And if people are taking the same course, you can't put them in the same time slot, right? How many time slots do you need at York so that no student is upset?
Bichromaticism is that it's one color on one edge and a different on the other edge.
Yeah, for every edge needs 2 different colors. Right? Right? So that's why when we're coloring, so those are important points at the beginning, right? So here you'll note every edge is bichromatic, right? It's a coloring. In fact, here it is. There exists a coloring that uses at most 6 colors, such that every edge has 2 different colors, right? And so that's true here. And what do I need to do? I need to find a color for this. Well, there are at most 5 colors here, because I only have 5 neighbors. So I color it with the 6th color. Right? Everybody go to that? And then now I've constructed I've constructed my coloring. Right? All right, so now what do I have to do? I have to prove that my coloring has at most 6 colors, right? My oracle assured me that her coloring only has 6 colors. And I made sure the deleted node got one of those colors, right? So I still have 6 colors, right? Everybody good with that? Right. Now what do I have to do? I have to prove that all edges are bichromatic. How do I do that? The adversary, right, gives me an edge, right? The adversary says, oh, you claim it's a good coloring. What about this edge? And you say, oh, I got to prove it's bichromatic. All right. Well, cases. Remember, everybody knows cases. There's 2 cases. The one case is the edge he gives me is one of them connected to the deleted node? And then I say, yeah, well, I made sure that the deleted node didn't have the same color as one of those nodes. So yes, these edges are bichromatic, right? And then I say case 2, the edge is from the smaller graph, right? And so then I come up to the oracle and I say, hey, oracle, the adversary gave me an edge. What do you say about it? And she says, don't panic. I gave it different colors, right? So you can go back and say, yeah, oracle, adversary, don't worry. The oracle promises me they have different colors, right? People see that? And we played the game and we proved it. So we proved the step of induction. So we proved that it's true for all I. So this completes that, right? So sometimes I wonder when I get to the bottom of the proof, what do I do? And foremost proofs kind of pop back. And here you'll see what I did was I kind of popped back and reminded people of the major steps, right? Right? What were the major steps? Well, we played the game, right? We played the game, so we proved it for SI. Then pop the stack. Well, hence we prove SI gives me SI minus 1, right? So, and we did that as well. So then we get it by induction, right? We kind of popping the major steps back and reminding people what we did. Right? Everybody good with that? What do you think about that proof? It wasn't as bad as I thought it was going to be. How many people, honestly, how many people could follow that? Right? You didn't follow it? Right. All right. Well, you can see how if you're going to be proving things and understanding things in math, that this is just important, right? Are people with me here? You think anybody, when they're writing up a proof of this, is going to do the formal proof, right? Nobody's going to do the formal proof, right? They're going to do some casual version of what we did here, right? In fact, what they'll do will be more casual than what we did. They'll do the high level, and periodically they'll say, well, obviously I have I minus 1 nodes because I deleted one. Obviously, a planar graph, when you delete a node, is still planar, right? They'll put in a couple obviouslies. And I think a couple obviouslies are good to do. It's you need to know who your audience is, right? If your audience are people where if you delete a node from a planar graph, know that it's still planar, then you don't have to say that, right? But if your audience might not know that, then you can go through the steps, right? You can put the proof in the appendix. All right, everybody good? Now, let's go back to, remember I had an argument with my stepmom about this problem, and I can't remember what I'm clear my position. I forget what she said that I didn't like. All right, but how is it recursion, right? I'm gonna be bad here, and I'm gonna micromanage my friends, right? But you shouldn't, right? So the adversary gives me as an input a graph that I need to color, and I delete a node of degree 5, right? And then I delete. I keep deleting nodes until I have no nodes, right? And then right, what's my base case? My favorite number is 0, right? If I have 0 nodes, how do I color it? The 0 coloring, right? And then we start popping back up the stack, right? We add back in the 1 node we deleted. We add back in the 2nd node, the 3rd node, right? we add them back one at a time. Right? Does that make sense? Now, everybody get it? That's how kind of recursion works. And when we have one friend, you go down and you come back up. Right? Now, if you might look at this, why did I, right? I'm going to say here somehow, don't micromanage your friends. Don't do this at home. Well, why can we do this so easily? Because we only have one friend, right? And it feels, on the way back up, feels like an iterative algorithm, right? And if I suspect what I didn't like my stepmother doing is it sounded like she was doing an iterative algorithm, right? And then so here, let me just tell you, I don't know of an iterative algorithm for it, right? And you say, well, what do you mean you don't know? Here's right here is an iterative algorithm, right? Anybody know what I don't know? I don't know which node to color first, right? I know which node to color last. The one to color last is the one with low degree. I don't know which one to cover first. All right? All right, so it feels iterative, right? Why not do that? Fantastic question. The key is every time a node is colored, we have to make sure that it's degree 5, right? When you're giving it a color, the smaller graph has to have degree 5, right? So you have to do it in an order in which that's always true, right? All right, so you say, well, suppose you have a graph. Suppose the oracle doesn't give you the adversary. Suppose the adversary doesn't give you a planar graph. Suppose the adversary only gives me a graph and promises that it has a node of degree 5, right? Can I color it? No, I can't color it, right? Here's some high degree graph that I don't know how to color. It has no coloring. I add one node here of low degree. It's not suddenly colorable, right? It's not colorable, right? Right. So here's some graphs, right? Here's right. There may be nodes of high degree, right? So we could say, well, certainly in this graph, give it a color first, right? And then we know how to color all the others, right? That's good, right? But it can be more complicated, right? So, right. So what do we use? Right. We are always using the fact that every planar graph is 5 colorable. It's not just that. Sorry, every planar graph has a low degree node. It's not just that this has a low degree node. It's that every time we delete something, it still has a low degree node, right? Can we apply the same algorithm, right? And the answer is no, right? Because suppose I was given this graph. What's true about this graph? It's a scary graph with high degree, right? But it has a low degree node. If I delete this low degree node, what do I have left? A scary graph, right? Right. So this says when you right, I'm given a graph with low degree. I delete it. I give the rest to my friend. Does it meet the precondition that it has a low degree node? No. Right? Graphs can have a node with 5 degree, and when you delete it, you have a scary graph. Right? That's what we're drawing here. Everybody buy this? All right. And that's it for graph coloring. That wasn't, you okay? Everybody okay? Yeah?
So could you go over what you said
At the end?
Yeah, this piece about degrees as it was 5 not being colorable?
Yeah. All right. So this node, what is this graph? this is a scary graph with high degree nodes, right? In fact, let's make this the complete graph. How many colors do you need to color the complete graph? Every node needs its own color, right? Because every node is connected to some other node, right? Every node here needs its own color. And then I add on one little node with low degree. Is this guy colorable? No, right? It has low degree. But what happens when I delete it? It's no longer the case, right? Now, in contrast, if this is a planar graph and this node has low degree, I delete this. This is still planar. So it still has a node of low degree, right?
Sorry, if you add a low degree, why is it not colorable?
With this one here?
You start off with complete, and you add that little low degree one with one vertex.
This needs in colors.
Right.
I add this.
Yeah.
Well, how many colors does it? If it's connected here to something red, then this can be blue, where we have a blue over here, right? So how many colors does this need?
N+1.
No, I don't know. I'm willing to say you don't need a new color,
Oh, okay.
right? It can still be, you can use a color you haven't seen before. You can use a color you had seen before. But it still needs a million colors.
Right.
Just doesn't need a million plus one.
Oh, I see.
Right? This is way bigger than 6.
Yeah. Oh, I see.
Right?
So in adding one, it is colorful.
No.
It's not 6 colors.
It's not 6 colorable.
Okay. Sorry, I didn't.
Yeah, it's every graph. The complete graph is colorable if you have in colors. Right? It's just not 6 colorable. Right? Everybody, yeah? All right. We went a little fast there. I do think maybe we should have gone, should I have gone slower? I think they might have let me go slower, right? Maybe watch the video again, slow it down, all right? Because it's just, what did we do there? All we did was we wrote down every statement as a first order logic statement, and we played the game. And if somebody was assuring us something was true, then if she had a for all, we gave her an object and she gave us back that exists, right? And if we were trying to prove it, if we have a for all, we got it from the adversary and we had to construct the exists. That's all we did, right? And you can kind of see why when my little brother came and gave me this problem I knew nothing about, and he helped me write it down in first order logic, then the proof just fell out, right? Everything, nothing, no step here was hard, right? Every step was, once you know I'm given a graph of size I and I want to delete someone, well, who do I delete? Well, I was told it has a low degree node, right? All right, ready for strong induction? You might have seen strong induction before, right? We have these SIs and we want to prove that they're all true, right? My goal is to prove that they're all true, right? And we're going to do it with strong induction. All right. So this is the statement of strong induction, what are the differences here? In order to prove I'm assured of everybody smaller, right? Not just the previous guy. I'm assured of everybody smaller, right? And this is when I say recursion is induction, really recursion is strong induction, right? And the funny little glitch is that we don't prove the base case anymore, right? All right, so where are we? Let's see, gotta get this to work again. All right, so we prove that, and then she proves it's true for all of them, right? All right, so how do we prove this? Well, it's a for all statement. So the adversary gives me an arbitrary I, right? And I have to prove S of I. But what do I have to help me? Right? I have, the oracle is promising me S of I like she was before, right? But she's a really nice oracle this time. She will promise me everything smaller than I, right? Does that make sense? And so it's only going to make my life easier, right? Before I only had, she was only promising me an S of I plus minus 1. Now she's promising me all the previous guys, right? Everybody get that? All right. So that's weak induction. And weak induction, the problem with what's the problem with weak induction? Is that if I want to prove that my recursive algorithm works for every input of size I, right? And then weak induction only assures me that inputs of size I minus 1 work, right? And but what do I give my friend recursively? I might give my friend something smaller, right? So the strong induction assures me of all previous, right? Does that make sense? That's helpful. Now, how did I avoid it before? As I defined S of I to be, it works for every input of size I or smaller, right? I put that into the S of I statement. And that's how I got away with using weak induction, right? Right, so here, before I said at most I. All right, so now I note here that we don't even have a base case, right? And that's just a little kludge. I mean, the truth is, when I'm proving induction, I'm gonna have, when I'm proving my recursive program works, I need to prove it works for the base cases, right? But why don't I have it here? Well, how does it work, right? I have to prove this statement here. And when I prove it, the adversary has to give me an arbitrary I, right? I have to prove this for every I. And the adversary could give me 0, right? And then what do I have to do? I have to prove S of 0, right? And what's the oracle assuring me? She's assuring me of nothing, right? There's nothing before, right? So I have nothing that being assured of, and I have to prove S of 0 all by myself, right? Does that make sense? So really, the bottom line is you got to prove S of 0. And I only didn't add it here for humor, right? And that is induction. All right, everybody good?